Hello everyone, my name is Zach Wen, and I'm a software engineer on the Presto team in Meta. Today we are excited to talk to you about the latest Prestissimo extension we built to support the AI training data normalization at Meta. This talk is brought to you by me, Wenqi Wu, and Xiaoxuan Meng. Here is our agenda. Wenqi will cover the first section, AI data storage overview, to give you some high-level context about the AI storage system in Meta. I'll deep dive into the extension we built in Presto/Prestissimo and some of its technical details. At last, we'll briefly share our future plan and open the floor for any questions you may have. Now, I will hand it over to Wenqi.
Hi, I'm Wenqi, and I'll be giving an overview on AI data storage. At Meta, training data is modeled as relational tables in data warehouse. Each table contains training samples, where each training sample comprises features and labels. Features and labels are stored as separate columns in the same table in a denormalized manner. During model training, training samples are sequentially read from tables and supplied to the GPUs. In recent years, the machine learning landscape has undergone some changes. There's growing adoption of user sequence modeling, where the recommendation models learn from user event sequences. These features are often much larger than traditional human-engineered features. With the rise of multimodal models, there is also a need to include more expensive data artifacts in training data, such as text, images, videos, and embeddings. There's also incentive to train models on larger volumes of data and more diverse datasets to improve model performance. All of these trends point to one thing: the need for an order of magnitude increase in the scale of training data. As mentioned earlier, training data is stored in a denormalized manner when training samples and features are in the same table. As the scale of training data grows, this approach presents several significant challenges. Firstly, there's a high storage cost, of which a large portion is attributed to duplication of feature data across training samples. Secondly, ML experimentation becomes slower and hinders the productivity of ML engineers. ML experimentation often requires incorporating new features into existing training data. For large datasets, this can be time-consuming and storage-intensive if the new features were to be row-by-row inserted into the same table. AI data storage enables training data to be stored in a normalized manner. This means that the features are stored in a separate table from training samples, significantly reducing the storage costs associated with high data duplication. The feature data can be efficiently retrieved from AI data storage via sequential and random reads. During ML training, training samples are sequentially read from data warehouse and joined with the corresponding feature data from AI data storage. Compute engines such as Presto and Spark are also capable of querying AI data storage, which is useful for ML data exploration scenarios. At the heart of AI data storage lies a robust set of capabilities that enable efficient and effective management of training data. These include seamless integration with Presto and Spark to support various SQL operations on tables, a tight integration of ML training stack to enable index join against tables, data versioning to ensure that feature data used for training is consistent with what was used for prediction to prevent feature leakage, ETL workflows for data ingestion, and various optimizations that exploit data and query patterns to improve performance and efficiency. Back to you, Zach.
Thank you, Wenqi, for the overview of the AI data normalization in Meta. Next, I'll talk about the Prestissimo extension we built to support the AI storage system. As he shared, in the system, AI training data is normalized and split into two datasets. More specifically, the feature data is stored in a new file format, SST, and has two copies, one in Hive and one in a key value store. So to provide an on-par feature analysis and training data debugging experiments for our machine learning engineers, we've made a few extensions in Presto. First, since AI feature data is now stored in SST file format, we've integrated a new SST reader and writer to perform sequential scan on the table. And so machine learning engineers have access to the tables and explore the feature data. Second, since the training data is now split and we need to join two datasets back to reconstruct the full training samples, we've also enabled join to perform random read on AI training data storage system. We use index lookup join for fast lookup. It currently supports two join types, inner and the left outer join. And it supports equal join condition and two non-equal join conditions, which are between and contains. This graph outlines the high-level components involved in Presto. On the coordinator side, we have an AI data storage connector, which is responsible for retrieving table metadata, resolving index, and performing connector filter pushdown. And there is an index join optimizer, which is a component that converts an eligible hash join into an index join. On the worker side, changes have been made to the plan conversion protocol to support new plan nodes like index join node, index source node, and the AI data storage connector related data structures, making sure the Presto query plan is able to be converted into a Velox query plan. And we've added an index join operator in Velox. This is used to perform lookup operation and provide index join execution support. And there is an AI data storage connector, which uses AI data storage client to take care of the I/O with the AI storage service. And on the sequential read path, as I mentioned, there is a SST file reader and writer added to enable Presto to access the feature data tables. On the coordinator, index join optimizer is a main component for the query planning. On a very high level, what it does is basically, first, it extracts the key columns from the query plan nodes and pass the index input columns to the SPI connector metadata resolve index. See if given the input columns, the results of requested output columns can be provided. If yes, an index can be resolved, then the regular join will be converted to an index join by replacing the join node with an index join node and the table scan node with an index source node. Other than the planner level optimizer, we've also added a connector level optimizer to push down the predicate in the filter node to the connector table handle. To make sure the Presto plan can be translated into a Velox plan, we've made some changes to the Prestissimo plan conversion protocol. A couple nuances here are basically in Velox, there is no index source node. So it reuses table scan as a plan node representation. Also, the join conditions are defined as a list of expressions. So we actually added a parser to parse the filter from the join node, making sure the plan can be executed by Velox successfully. After a Velox plan is generated, the Velox planner, local planner, will convert the plan into a executable pipeline. One of the main differences between index lookup join and other join strategies is other join strategies like hash join, merge join usually have two downstream pipelines, one prob and one build pipeline. and they are connected by a join bridge. Both downstream pipelines generate results, and the operator will join the results like through some matching mechanism. However, index lookup join only has like one single downstream pipeline. It basically pulls data from its downstream pipeline and based on the index, performs lookup inside the operator itself to retrieve the matching records and produces the output rows. Each connector can define its own lookup logic by implementing a new connector interface index source. And we've also added prefetch support, which can be enabled by a session property. How does prefetch work? Is basically, each operator has two functions, one add input and one get output. The index lookup join operator can start fetching the results and hold the results for multiple lookup requests before them get actually requested by its upstream operator through a get output function. Regarding our future plan, the AI data storage system improves the storage efficiency, but in the cost of compute with an additional join. So far, the work we've made has been around the functionality, basically, to enable the capabilities in Presto. Next, we'll shift our focus to the performance and scalability to support larger scale AI workloads. We are currently exploring ideas like sort merge join to minimize the compute cost this new storage system introduces. That's all from us. We would now like to open the floor for any questions you may have about the Prestissimo extension or our approach to AI training data normalization.